Hello and greetings you all. We are AS1202J, Diploma in Science of UiTM Pahang Campus Jengka student. We would like to present you about our third assessment of MAT183. Before that, let's get to know our group members. There are 5 of us. Dia Humaira, Putri Kota Aini, which is me, Nur Anwar Afika, Wan Zarid Sofia, and also Arina Nadira. So, what is applied maximum and minimum problems? In mathematical terms, maximum and minimum refer to the highest and lowest point on a graph of a function. When these points occur within a given interval, they are called local maxima and minima. The absolute highest or lowest point on the entire graph are known as global maxima and minima. There are a few steps to complete a solution. First, define the function. Formulate the function that needs to be optimized based on the problem's condition. Second, find the derivative. Compute the first derivative of the function. Third, identify critical points. Set the first derivative to 0 and solve for the variable to find critical points. Fourth, second derivative test. Use the second derivative to determine the concavity of the function at the critical points. Fifth, analyze the results. Evaluate the function at the critical points and endpoints of the interval to determine the absolute maxima and also minima.
Let's take a look on question 10. An open-top cylindrical can is filled with 50 cm3 of water. A. Show that the total surface area of the can is A equal to pi r squared plus 100 over r. B. Find the minimum surface area needed to manufacture the can.
In this part, the question asks us to show that the total surface area of the can is A equals to pi r squared plus 100 over r. So, the first step is we know that the volume V of the water in the can is given by V equals to pi r squared H. And the volume of water is V equals to 50 cm cubed. We're gonna let R to be the radius of the base of the can and H would be the height of the can. So, volume of the can is V equals to pi r squared H and V equals to 50. So by solving H, we will get H equals to 50 over pi r squared. Since the can is an open top, the surface area A is gonna include the base and the side. So the equation would be A equals to area of the base plus area of the side. We know that area of the base would be pi r squared and area of the side 2 pi r h. So it would be A equals to pi r squared plus 2 pi r h. Last step, we're gonna substituting H from the volume equations. So from A equals to pi r squared plus 2 pi r h, then substituting H equals to 50 over pi r squared, it would be A equals to pi r squared plus 2 pi r 50 over pi r squared. If you see this closely, we can actually cancel out the 2 pi r, the pi r, and 50 pi r squared, the pi r squared, making it only leave the r behind. Then we can times up the 50 and 2 would be 100. So the last answer would be A equals to pi r squared plus 100 over r. Thus, this is the total surface area.
To find the minimum surface area, we need to find the critical points of A with respect to R. We do this by taking the derivative of A with respect to R and setting it to 0. The surface area A of the can includes the bottom and the side of a rectangle wrapped around the circle. Using the volume constraint, we express the height in terms of the radius R. The surface area A is given by A equals to pi r squared plus 100 over r. We need to use calculus to find the radius r that minimizes A. This involves taking the derivative of A with respect to r, setting it to 0 and solving for r. The critical point is r equals to 50 over pi to the power of 1 over 3, approaches 2.51. Next, Next, we need to ensure this is a minimum by checking the second derivative. If the second derivative is positive at the critical point, it confirms that we have a minimum. With the radius found, we calculate the exact surface area by substituting this radius back into the original surface area formula. Through this process, we find that the radius r approaches 2.51 centimeters, resulting in the minimum surface area. The corresponding height can be calculated using the volume formula, and then we determine that the minimum surface area required to manufacture the can is approximately 59.63 centimeters square.
In conclusion, our exploration of applied maximum and minimum problems has highlighted the power of calculus in solving real-world optimization challenges. By understanding how to identify critical points and evaluate the nature of these points using derivative, we can find the most efficient solution to practical problems. Here is our recap. First, confirming the minimum. Second, minimizing the surface area. Third, setting up the problem. And the last one, finding the surface area formula. By following these steps, we found the optimal design for the can, showing how powerful calculus can be in practical applications.
And here are some of the references we used.
And with that, that's the end of our video. Thank you!